So in this class we are going to discuss about the digital signature algorithm. So previously we have discussed about the hash based algorithms. So the message digest, that is the SHA-256, SHA-512, HMAC algorithms being discussed. So digital signature algorithm is based on the is used for authentication mechanisms, and it is based on the hash based mechanisms. So digital signature is a mathematical technique used to validate the authenticity and the integrity of a message, software or digital document. So to authenticate a document, we use the digital signatures. So one basic important difference between the MAC and the digital signature is that the MAC uses the symmetric key, whereas the digital signature uses the public key cryptography. So it uses the private key and the public key. So digital signatures, we have looked at the message authentication, but does not address the issues of the lack of trust. Digital signatures provide the ability to verify the author, date and time of the signature, authenticate message contents, be verified with third party source disputes. And this include authentication function with additional capabilities. So here what happens is that it will be doing only the authentication function, but it cannot verify the confidentiality or the message being modified or not cannot be looked into. So here we need to do some other cases like encryptions also. So this is to provide that this message belongs to this person, like that it is only an identity. But what happens is that the message is also been added along with this digital signatures, and then it has been transmitted. So the message is originality cannot be protected using the digital signature. So digital signature is not an encryption algorithm. It cannot protect the message that has been added along with this message, this signature. So that is the problem. So this is the digital signature model, and we have the Bob would be transmitting and Alice will be receiving. So here we have the message, and the digital signature signed by the Bob's private key is also been added, and Bob's signature is added along with the message. The message is in open. So how can you protect the message? The message cannot be protected. So here in addition we need to perform some encryption. Only thing is that we can verify whether the message is been modified or not. Okay, but the message cannot be completely be secure. So but here it can be verified. So the signature can be verified. Again the message has been applied to the digital signature verification algorithm, and then the return signature is valid or not, it can be identified. So this is the model, and the message is applied to the cryptographic hash function. So a hash has been generated. It has been encrypted using the private key of Bob, and Bob's signature has been created, and it has been added along with this message. So again the received message has been applied to the cryptographic hash function, and a hash has been received, and the signature has been decrypted, and we will be getting the hash dash, and it has been compared with both the cases. Then we can get this one as the valid or not. So for decryption we use the public key, Bob's public key. So that is the sender's public key can be used for verification, whereas for encryption of the hash, then it can be using the private key of the sender. So only the sender's keys alone is being used. Okay. So now we have the key only attack. There are different kinds of the key attacks are there. One is the key only attack, or the known message attack, and generic chosen message attack, and directed chosen message attack, and adaptive chosen message attack. And here also the based on the success, when we can have the complete universal breakdown or complete universal forgery or selective forgery or existential forgery, like that we have different kinds of cases are available. And here what happens is that here the first case is the key only attack, only the key has to be if the public key alone is being known, with that we need to attack. And in the second case we have some portions of the message is also being known, and with that then it could be attacked. So the known message attack. Then we have the chosen message attack. In the case of the chosen message attack, we can directly insert the messages. So generic chosen message attack, directed chosen message attack, adaptive chosen message attack. Like that we have different kinds of the insertions possible, and it can be verified. So similarly here we have the total break or the universal forgery. It can be breaking any, the entire algorithm would be broken. And in case of the selective forgery, only a portion of the message can be identified, and so based on the selection. And in existential, it can have breaking for only one plain text, ciphertext pair. So that is the case of the existential array forgery. It cannot be applied for any other plain text or ciphertext pair. So it has been attacking only that particular message and the ciphertext. So that is the case. So it is subjected to only one message. It cannot be extended to any other messages. So if it is applied, then it will be failing. So like that, it is existential forgery. And the digital signature requirements. It must depend upon the message signed. It uses the information unique to the sender, and it must be relatively easy to produce and easy to recognize and verify, but it is computationally infeasible to forge with a new message for existing digital signature or with the fraudulent digital signature for a given message. So all these things these are all the basic qualities of the hashing, and already we have discussed the hashing in detail. Okay. So here also we have the message has been signed, the contents of the message is used for digital signatures, and the sender's information is also been added, so that it becomes more distinct. It cannot be used by any other person. It is practical to save the digital signatures. So there are two kinds of the one is the direct digital signatures. It involves only the sender and the receiver. It assumes the receiver has sender's public key, and it uses the digital signature made by sender signing the entire message or hash with the private key. Can encrypt using receiver's public key. And important that sign first, then encrypt the message and signature. So this is the direct digital signature. It assumes the receiver has the sender's public key. So here we have the private key is being used for encryption purposes, encryption of the message or the hash, and the decryption can be done by means of public key. So first signing and then encryption. So one more type is that thing, but it is going to be the LGAML digital signature. The LGAML digital signature, it uses the it also uses LGAML based certification. It uses the Galife field and the modular exponentiation. So based on the LGAML digital signatures, the digital signature standard has been designed upon, and we have the NIST and the NSA has designed this one, and it has been published and revised. And one feature is that it uses the SHA hash algorithm, and the DSS is the standard and DSA is the algorithm. So it can have an alternative of RSA and elliptic curved signature variants. So DSA is a digital signature only, unlike the RSA. RSA is nothing but in encryption algorithm, but it is a public key technique similar to RSA. So there are two kinds of versions of the DSS and the RSA. In the RSA, the message is being applied the hash function and it has been encrypted using the private key, and it has been concatenated with the message. So the message and the encrypted hash is being sent. At the receiver, the message is applied the hash function and it has been compared with the received hash being decrypted by means of the public key of the user A. That is the RSA based approach. Whereas in the DSS approach, what happens is that here we have the message and the hash is also been applied, and a global public key is also been applied, and user A's private key is also been used for signing the algorithm, and it also uses the key. Based on these concepts, then the digital signature has been produced, and it will be having two components. One is S and the R, and they are concatenated with the message. Again, the message is being hashed, and then it is being verified with the S and R components being decrypted using the public key, global public key, and also the user's public key. So then finally it is been verified. So R is being compared and it has been verified, and it has been decrypted using the public keys at the other end, and finally it will be compared and verified. So this is the DSS approach. So it is a complicated approach where it uses the modular exponentiation, the prime numbers and other things. So DSA would be creating the 320-bit signature or 160-bit signature based on the SHA values, and then we have the 512 to 1024-bit security. It is smaller and faster than the RSA because it is not encrypting the entire message, only the hash value is being encrypted. So the size is small, and so it is much faster than the RSA. And it is a digital signature scheme alone, not encryption. And the security depends on the difficulty of computing the discrete logarithms, and it is a variant of Elgamal and Schnorr schemes. So the steps to be followed: the message register is computed by applying the hash function on the message, and then the message register is encrypted using the private key of the sender to form the digital signature. So the digital signature is then transmitted with the message, and the receiver decrypts the digital signature using the public key of the sender. And the receiver now has the message register. The receiver can compute the message register from the message, and the message register is computed by the receiver, and the message register obtained can be compared, and if it is same, then it ensures the integrity. So the DSA key generation, it uses the 160-bit prime number Q, and it choose a large prime number P, where P ranges from 2 power L to 2 power L minus 1, where L ranges from 512 to 1024 bits, and it's a multiple of 64. So Q is nothing but the 160-bit prime divisor of P minus 1. So large prime number of 512 to 1024 bits is being selected, and the prime divisor of P minus 1 is being Q, and its length is considered to be 160 bit approximately, and then we have the G is being computed. G is nothing but it is going to be H power P minus 1 by Q, where H ranges from 1 to P minus 1, and H power P minus 1 by Q mod P must be greater than 1. So based on these conditions, the H can be selected, and the G is also been computed, and then we have the random private key X is being generated, and the public key is also been computed based on the private key. So G power X mod P is the public key, that is Y. Y is the public key and X is the private key, And to sign the message, a random signature key has been selected, K has been selected where K is less than Q, and K must be random and be destroyed after use and never to be reused. So for each message, then it has to be generated, and then we have to compute the signature pair R and S. R is equal to G power K mod P mod Q, and the S is nothing but going to be K inverse H of M plus XR mod Q. And sends the signature R, S with the message. So the signature is nothing but it is going to be the R and S component. So the DSA signature verification, having received the message and the signature, to verify the signature, the recipient computes W, U1, U2 and V. And if V is equal to R, then the signature is verified. So W is nothing but can be S inverse mod Q, and U1 is H of M W mod Q, and U2 is RW mod Q. V is nothing but can be G power U1 Y power U2 mod P mod Q. So if V is R, then the signature is verified. So this is the DSS overview. So here we have the complicated functions being applied to generate the signature S, R. And for verification also we have complex functions has been applied and it has been verified. So it is a very powerful standard. So digital signature versus the digital certificate. So later we will be discussing about the digital certificate, and what happens is that now we have the digital signature. So digital signature is like a fingerprint or an attachment to a digital document that ensures its authenticity and integrity. But digital certificate is a file that ensures holder's identity and provides security. So digital certificate can be separately sent. So if you needed to verify the identity, the digital certificate can be sent, and that provides the identity of the user. But digital signature is for that particular message, it has been sent, it has to be generated and it has to be attached along with the message, and then it verifies the message being provided by the user or not. So the hashed value of the original message is encrypted with the sender secret key to generate the digital signature, whereas the digital certificate is provided by the certificating authority, and that involves 4 steps: key generation, registration, verification and creation. And the security services, authenticity of the sender, integrity of the document and non-repudiation can be verified using the digital signature, and it provides security and authenticity of the certificate holder, whether the certificate holder is authentified user, whether the data communication can be secure or not, can be verified using the digital certificate. And the standard is nothing but can be digital signature standard, and here we'll be studying the X.509 standard format. So this X.509 we'll be discussing in the 4th unit. Thank you.